Okay, so next thing about probability is binomial process. Um, so binomial process happens when we have only two possible outcomes, and yes or no, on or off, right or wrong. In a birth, we have boy or girl, and the other example with the push pin that I said before, okay? Unless it's very rare that the pushpin is going to get stuck just like that. I never saw that happen. You know what? I can say the surface is metal, so definitely it's not going to stuck uh, heads up like this. So this is not going to happen. So we have two possibilities. Now the important thing is that there are two possibilities. It doesn't have to be, I'm sorry, there we go. It doesn't have to be 50-50 chance. So, but there are only two possible outcomes. Okay, so this is one condition for using binomial process, and trial outcomes are independent. So for example, what does this mean independent? When you toss a coin, the second result is not affected by the first result. Some people think, okay, the coin landed heads up 10 times. There is no chance or very, very low probability that it's going to land again heads up. And that's not true. The probability is always 1 over 2, 50%. So it is not the new toss is not affected by the previous one or any of those before. But if I give you a deck of cards, okay, this is deck of cards, and I tell you draw a card. You don't see the cards. I tell you draw a card, and you draw the ace. Okay, ace of hearts. Okay, you drew the ace of hearts. And the probability for that, by the way, since we have 52 cards in the deck, not including the jokers, so we have 1 over 52. So now I can put the card back, shuffle the deck, and ask you to draw another one, and ask you what's the probability for the Queen of Hearts. So it's going to be again 1 out of 52. So these two events are independent. But if I will keep the Ace of Hearts outside, okay, and now I tell you, draw another card, what is the probability it's going to be the Queen of Hearts? So we have only one Queen of Hearts left, okay, but now we have 51 cards in the deck. So the probability is now 1 out of 51 for the Queen of Hearts in the second draw if we did not replace the Ace of Hearts in the deck. So in this case, if you keep on drawing without putting back the cards and shuffle, of course, then the two events are dependent. But if you keep on putting the card back and shuffle, the events are independent when you have to draw a card. So the second condition is that each trial has to be independent. The trials are independent. None of them depends on the previous one, on the previous trial. So this equation looks a little bit complicated, but we're going to solve it, or I'm going to explain it in a moment. And for this, I'm going to explain separately the meaning of factorial. You might have met that operation, and let me just open a new slide here. So let me start with an example, and I'll start with a few examples. So I'm going to write 5 factorial. 5 factorials is the product of all numbers from 5 all the way down to 1. So 5 times 4 times 3 times 2 times 1. And 100 factorial will be 100 times 99 times all the way down to 2 and 1. Sometimes I will omit the 1 because it's obviously we don't need to multiply by 1. Important thing to know is that even though it doesn't sound it doesn't sound like it makes sense, 0 factorial is equal to 1. Okay, I know it doesn't. It sounds like it doesn't make sense. I'm not going to explain the rationale behind it, but I'm going to tell you that it's very similar to 7 to the power of 0, which equals to 1, or any number except of 0 to the power of 0 equals to 1. So let's just accept it now as 0 factorial equals to 1. And all the rest you already know. So the formula in general will be n factorial equals the number n times the number n minus 1 times the number n minus 2. And I'm not going to go all the way down to times 2 times 1. Okay, obviously I don't know what's n, so but this is the general formula for a factorial. Okay, so let's go back to the formula here. And this is the probability, and we'll see in a moment a question that refers that we have to use this equation. Okay, so you know what? Let's go back to the question, and let's go to the question, and then I'll go back to the equation itself. This is the same formula that you see here, just this part right here. This part right here is this part of the equation that you see right here. Okay, so it looks a little bit different, but it's the same. Basically, it's the same equation. Okay, so this is the question. What is the probability of tossing a coin 3 times and landing heads up 2 times? So obviously we know how to solve it. I think we solve landing heads up. No, before we had exactly 2 times. Okay, so let's go on and solve the problem. Let's go here. So the probability is the thing that we have to calculate. Okay, so I'm going back. We have to find that probability. Second number is the number of times for a specific outcome within n trial. So the number of times that a specific outcome, which is lending heads up 2 times. Okay, so in our case, x equals 2. The next item that we need, the next variable, is the number of trials. So let's go back, number of trials, right here. Let's go back to our equation here, or the problem. What is the probability of tossing a coin 3 times? So the number of trials, we have 3 trials here. Okay, so I'm going back here, and n equals 3. The next thing that we need, the probability of success on a single trial. Now, success is what we define as success. Sometimes it might be failure in real life, but the event is successful. We define what is success. We can define that missing a shot to the basketball shot will be a success. Okay, if we want to count how many times you will miss, then missing will be a success. So again, success is what we define as a success, and in our case, lending heads up 2 times, success will be lending heads up. Okay, what is the probability of lending heads up? The probability is 0.5. This is the probability of lending heads up. The other number, Q, the other variable, is probability of failure. So if success is 50% or 0.5, our failure is also 0.5. The failure is always completing the success to 1. So I can write it here. The probability that the event will not happen equals to 1 minus the probability that the event will happen. Okay, so obviously here, 1 minus 0.5 is 0.5. So I think we have enough. Yeah, we have all the variables that we need. So let's start with the calculation here. So let me just move. Sorry. I'll move this part here. And this is our equation. I'm going to erase. And let's just plug in the numbers. So back here, the probability is, again, x is the number of successes. So again, tossing a coin 3 times and landing heads up 2 times. So we have the number of trials is 3, n is the number of trials, 3 factorial. We're going to calculate it in a moment. And then we have p to the power of x. So we have 0.5 to the power of 2. And this is 2. And then we have q, which is also 0.5 to the power of n minus x, which is 3 minus 2. I'm going to write it as is. I'm not going to calculate it yet. We'll calculate everything later. Right now, we just plug in. And this is over x factorial, which is 2 factorial, times n minus x, 3 minus 2 factorial. So let's do one step at a time. 3 factorial is 3 times 2 times 1, which is 6. So we have here, let me write it here. This is going to be 6 times 0.5 squared is 0.25. And then we have 0.5 to the power of 1, which is just 0.5. This is our numerator. 3 items, 1, 2, 3. 3 items here, 1, 2, and 3. And denominator, we have 2 factorial, which is 2 times 1, which is 2. And then we have 3 minus 2, which is 1. 1 factorial is 1. So everything here is, we're almost done. This is the part where you can use the calculator, or you can do mental math, whatever you choose. The answer here is supposed to be 0.75. Let's calculate it. So we have 6 times 0.25 times it did 66, I'm sorry. So 6 times 0.25 times 0.5, 0.75 over 2. And this is 3/4. 3/4 over 2 is 3/8. Okay. And if you remember, it's very similar to what we got right here, 3/8. Okay. So basically, it's the same question. So 3/8, and that's it. And that was, I think, 0.375. 0.375. If you want, again, you can write it in 3 to 8 or 37.5%, but I'm not going to write all options right now. Now here they didn't ask exactly, and there should be another step for the lending heads up 3 times, which should be included if they don't ask exactly the point here. But I'm not going to do it. I'm going to solve this question as if the question was exactly 2 times, because we didn't learn yet, or what do we do when it's this or that. So here we have 2 times, exactly 2 times, or 3 times, which is the additional option. I'm going to solve this question as if it was exactly 2 times. Law of large numbers. So the more trials that are conducted, the closer the results become to the theoretical probability. What does it mean? If you toss a coin 5 times, so you might get 3 heads and 2 tails. And even if it's 6 times, and if it's another time, it might not be even to the theoretical probability. which is 3 and 3 as we accept. So we might get another result heads up. So we have heads, 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 tails, tails, and in this case, it's 2 out of 6, or 33, or 1 out of 3, or 33.33%. So you can toss a coin 10 times, and it might land all 10 heads up, even if it's a fair coin, which means it's not weighted. It's a regular coin that has 50-50 chance theoretical probability. But the larger the trials, if you will toss it 1,000 times, it is less likely that it's going to land heads up 1,000 times. If you toss it 1,000,000 times, it's going to get closer and closer to the theoretical probability. You see, this is an example of tossing a coin. So here you toss it 5 times. Let me erase my additional here. 5 times you get 0.6 for landing heads up. But if you toss it 500 times, the result will be closer to the theoretical probability, which is 50%. Here you're getting 50.2%. But as you go more and more with the trials. If you go 5,000 times, you might get to the number 50.001%. or 49.9997%. So it's getting closer and closer to 50% as the number increases. Law of large numbers. Okay, so let's continue with that. Probability. So how do we convert and or in probability to math? So again, we're talking about independent events. It works in independent events. In dependent events, the calculation is different, but dependent events are out of the scope of this course, especially in most cases with ands or. So we're going to skip it we're going to skip the math of it right now. If you take a statistics and probability course separately from engineering, just a course by itself, you will learn what to do in case the events are dependent. But again, it's not in the scope of our course. So, for example, if we have the probability of event A and B to happen, the result is the probability of A times the probability of B. So, for example, what is the probability that the coin, let's say the experiment is this. You toss a coin and then you roll a die. And my question is this. What is the probability that the die number will show 2 and the coin will show heads up? Okay, so this will be A. And I write here equal. It's not the probability, but this is the result. So this will be event A, this will be event B. So the probability for 2 on the die is 1 out of 6. We already know that. Each number has the same probability. Theoretical probability is 1 out of 6. And for the coin is 1 out of, the probability is 1 out of 2. Probability of head on the coin is 1 out of 2, or half. So now, if my question is, what is the probability to get 2 on the coin and heads on the, 2 on the die and heads on the coin, the probability will be the product of the two probabilities. And in our case, it's going to be event A is probability of A is 6, and probability of heads for the coin will be half. And we multiply numerator by numerator, denominator by denominator, and the probability is 1 out of 12. Okay, to have both die shows 2, coin shows heads up. So let's see an example. What is the probability rolling 4 on a single die? So we have 6 possible outcomes. We have 6 possible outcomes, and we have 1 desirable outcome. Get 4. There is only one option to get 4. So the probability is going to be 1 out of 1 out of 6. What is the probability of rolling 1 on a single die? So it's the same case. We have one desirable outcome, which is 1. We have 6 possible outcomes, and the probability for 1 is also 1 out of 6. And now the question is, what is the probability of rolling? Let me write here. This is probability for 4. This is the probability for 1. So what is the probability of rolling 4 and then a 1 in sequential rolls? So we have probability of 4. We calculated it to be 1 out of 6. 1 out of 6 for the 1. Probability of 1. And the answer is 1 out of 36. So probability of 2 events to happen simultaneously, the first one and the second one, or 2 consecutive events to not necessarily simultaneously, but consecutive. One happened and then the second one also happens. So it's 1 out of 6, 1 out of 6. You multiply them, 1 out of 36. Now, what do we do with or? What is the probability to event happen or the other event will happen, not necessarily end this one or this one. So here, and again, we're talking about independent events. One event does not affect the next one. So the probability will be the sum of the two probabilities. So let's see the same story. What is the probability of rolling 4 on a single die? We know this is 1 out of 6. We did it before. What is the probability of rolling 1 on a single die? It's also 1 out of 6. And what is the probability of rolling 4 or a 1? So in this case, we're adding the probabilities, and we have 1 out of 6 plus 1 out of 6, which is 2 out of 6. Okay, or 1 out of 3, or 33.33% or 0.33 infinite. Okay, so so this is how we calculate probability of or. Again, I mentioned it before, but a probability of an event not to happen is 1 minus the probability of the event to happen. So if I ask you what is the probability of not rolling a 1 on a die, so there are 2 options. There is a long way to solve it and a short way. So the long way is what you have to, not rolling a 1 means rolling 2 or 3 or 4 or 5 or 6. Okay, that's the meaning of not rolling a 1. So we already know that this is 1 out of 6, 1 out of 6, 1 out of 6, 5 times, it's 5 out of 6. But it involves adding a lot of numbers. Or we solve the probability of rolling 1. So we already know that the probability for 1 is 1 out of 6. And the probability for not 1 is 1 equals to 1 minus the probability of 1, which is 1 minus 1 out of 6, which is 5 out of 6. You might want to say, but it's the same thing. I can do mental math and add this and know that this is 5 out of 6. You're right, but this is an easy story. Here we have all probabilities are equal, and sometimes they're not all equal, so you have to add different fractions here, and it's not going to be as easy as doing it this way. So just get used to, if the question is not something, calculate what is the probability that it will happen, and then just do 1 minus that number. Okay, so I have some examples that we're going to try here, and this is again a deck of cards. And let's see, we have 4 different. In a deck of cards, we have 52 cards altogether. Again, we made the jokers. We can do it with jokers, but in most cases, the questions about cards are without the jokers. So we have 4 different shapes. We have the clubs, we have the spades, we have the hearts, and we have the diamond. We have 2 different colors. Okay, we have black, we have red. we have 10 different numbers. The ace usually counts as 1. Okay, so we have 10 different numbers. We have 3 different face cards. Okay, jacks, queens, and kings. The jack, the queen, and the king, one of each color. But these are called face cards. All of these cards, okay, all of these group here of 12 cards are called face cards. So let's see an example. So simple calculations. What is the probability that if we, again, the deck is shuffled, is placed back up so you don't see the cards, and you draw a card randomly. So what is the probability that you draw an ace? So in this case, we have 52 cards altogether, and we have 4 aces. Okay, 4 aces. So desirable is an ace. Okay, and all possible outcomes is 52 other cards. So it's 4 out of 52, or I think it's 1 out of 13 if you reduce it. And again, if you're not asked to reduce, you don't have to reduce. But read the instructions. If the instructions ask to reduce, then you probably want to reduce it. What is the probability of drawing a heart card? So we have 1, 2, 3, we have 13 hearts, 10 numbers, 3 faces. So we have 13 hearts, okay? And altogether we have 52 cards, and this will be 1 over 4 to reduce it. What is the probability of drawing a black card? So we have altogether 26 black cards, okay? Out of 52, 26 black, desirable, 52 possible, and we have half. Obviously, half of the cards are black, so the probability is 50-50. A face card. We have 12 face cards. And we have, again, the denominator is always 52. In this case, so we have the face card is going to be 12 out of 52. And I think this will reduce to 6 out of 20. No, this is 26. Yeah, and we can reduce it again to 3 over 30. Am I right? Divided by 2, divided by 2, divided by 2, divided by 2. Yeah, very good. So 3 out of 13. What is the probability of drawing a red 9? So we have 2 red 9s, this one and this one. Okay, so we have 2 desirable outcomes over 52 possible outcomes, and the answer is 1 out of 26. So this is the example with cards.